So, good afternoon, everyone, and welcome to the 8th session of the first edition of the Técnico MasterTalks. My name is Carolina, and I'm a master student here from Técnico, and today we'll be presenting a session from the Department of Mathematics. In the end, we have some time for your questions in the end of the talk, and then I encourage you to go outside. We'll have some the course departments that you can talk about with the coordinators, and we'll also have some student support unit for answer to your questions, and also some international career opportunities and international opportunities if you want to pursue in your master. So first, thank you, Professor Patrícia Gonçalves, to accepting our invitation to be here today. So Professor Patrícia is a full professor here in the Department of Mathematics, and she has published around 70 scientific articles in the field of mathematics, and also has won several research grants from FCT, Carlos Gulbenkian Foundation, and even the European Research Council. She was also Vice President of the Portuguese Mathematical Society in 2021 and was named corresponding member of the Lisbon Academy of Science in 2023. So we'll have the pleasure today to hear Professor Patrícia talk about how to obtain universal patterns that model the evolution of microscopic physical models from microscopic models. So, Professor?
Thank you very much. So I would like to thank everybody that was involved in these events. I think they are very, very nice. I'm just a little bit concerned about my mathematics students, let's say, because I see that the audience is a little bit low. But in any case, I want to give you in 30 minutes a little bit about, I want to tell you, let's say, a story. I will start with a story about how did I end up here? What I have been doing since my, let's say, high school studies, and what I do, let's say, research-wise. What is my research about? So, before we go to the real slides, let me show you that I come from a very small city in the north of Portugal. I think that everybody knows. It's the city of Barcelos. And, it's a small city in the north, very close to Braga. And I did all my studies before the bachelor in different schools in Barcelos, and then in 1997 I went to the bachelor in mathematics at the Faculty of Science in Porto, and I did it. I was passionate, in fact, by mathematics even in high school. One of my passions was medicine, and when I entered let's say the bachelor degree in mathematics in 97, we were 140 students at the time. We were really a very huge classroom, and there was maybe 90% of women and maybe 10% of men. And at the time, the bachelor, it was before Bologna, and what we used to do, at the third year of the bachelor, we had to choose a branch. And I did the two of them, pure and applied, pure and educational mathematics. And in the last year of the bachelor, my professors, they were telling me, I did my PhD at IMPA. They were asking, what are you going to do after? I did my PhD at IMPA. Maybe you should go there and try to see what you think about it. So from January to March 2022, you see I was still a student, and this is the big exam period that we used to have in Portugal at that time. And I decided to go for a summer course at IMPA. And then I decided to do some course which I'm teaching right now, which is measure theory. I have some of my students here. And the instructor at the time was Claudio Landim, and then I made a decision I should go to IMPA to do a PhD, and that's what I did. So just after, in 2003, January, I went to Brazil. I did a PhD in probability. And what I will explain to you today, I hope in the biggest part of my talk, is what I learned and what I'm still doing with the things I learned, which I'm passionate for, since 2007. All right, so after that, you also know probably that the life of an academic is not very easy. So after that, I took 2 postdoctoral positions, one in 2007, immediately after the PhD, at University of São Paulo with Pablo Ferrari, and in 2008, one postdoc position in the Mathematics Center in Braga, with the supervision of Alberto Pinto. Maybe some of you know him. He's a professor and a researcher in dynamical systems. And then I went to many, many places, so I just put here I tried to be a very short list. So I went to, maybe you know this place, it's here. in fact, I'm talking about different places, and also I'm going to talk about Técnico. But you see here the Faculty of Science and Technology on the other side of the river. I was there a professor. I went back to IMPA. I went to the University of Minho. These was all research positions. Then I went to the Catholic University, which is this one, in Rio, as a professor. And then in 2016, as you see over there, I started my life here in Técnico, and this is what I will focus on now. So since 2016, I'm here, basically 8 years ago. And then in 2019, I became a full professor. So what I've been doing at Técnico. So what do? I do research in the fields of probability and stochastic processes. I've lectured some courses in probability theory and measure theory. I supervise research projects, let's say master thesis, PhD thesis, postdoctoral fellows, and even research initiation grants, as I'm supervising one now of Eduardo. And I got, well, this was possible basically because, well, part of this, because I got this ERC starting grant that was mentioned by Carolina in 2016, which was really very nice. This is one of these European millionary grants that you get more than, well, it was more than 1 million euros to create a team of people to work in the projects that I will show you. And I gave a talk at ICM, which I think that if I can, I suggest that if you have a chance to go to ICM once in life, do it. It's really something inspiring. Even though it was 2022, and it was because it was supposed to be in St. Petersburg, so it didn't really happen the way it should have been, I recommend you to go. It's really inspiring, and for me it was. What else? I'm an associate editor and editor-in-chief in some journals in probability, and I have some administrative positions at IST, and if you want to ask, if you don't know what are any of these terms, you have, after these 30 minutes of talk, you can ask me questions about whatever is not clear, all right? So, okay, and here I say you can see also my webpage in case you have interest. What else is very important, and I also think that for students that want to pursue a research life, it's very nice when you keep doing this, because since I was in very different places along my academic path, I did some international collaborations, which I think it's really how to make maths go on, is that you make collaborations with people with different, let's say, with different background, with different expertise. And this is good because at the end, you share knowledge. And this is the most important thing. So typically when I do not know something from a different field that by some chance, I see it in whatever I'm doing, I ask one of these people, but do you know how to do this? And I think this is very important because my field of research intersects with many different fields in mathematics, as I will show you. So what do I do? And this is just a very short slide, and then I will really go to the details. My research field is called interacting particle systems. And basically, there are three main questions to answer. I will explain this later. I will show you simulations. But basically, imagine that you have particles that move randomly, and the dynamics is conserving some quantity. And you say, all right, it is conserved, but they move. So they change with space and time. And what we want to understand is what is the equation that is telling me how this quantity is evolving in space and time. And this is what is called the hydrodynamic limit, which I will explain later. Another question is that, so if this, let's say, if this solution that you see here on the board is the typical one, is the one that I expect to observe, but since my system is random, maybe I'm not seeing exactly that. When I look at the particles, I do not see exactly this line here, but I see something which is fluctuating around this line. And one of the questions is how to describe these fluctuations around the typical thing that I would like to, that I'm supposed to observe. Another thing, another question, so this is what is called hydrodynamics, fluctuations, and I go to large deviations. So imagine that you know that what you are expecting is the blue line, but for some reason, you look at your experiment and you see the purple one. So you make a question. This is not typical, but can I compute what is the price to observe this? And this is what is done in large deviations. All right, my goal, because I'm the only person working in Portugal, well, me and my students in this topic, And my goal is to create really a research team, you know, to put some mark on the map to say that, well, Portugal also works in this type of projects. All right, but if you want to know more, we need to go to other slides. So I'm going to change my slides. But before that, I just want to tell you, let's say from the personal side, from the family side, that I'm very proud of being the mother of 3 kids. And all of them, so especially the oldest one, asks me many times, why do you stay the whole day working in mathematics? How is it possible? It's very hard for a 12-year-old kid to understand it. But it's really because I'm passionate by what I do. So now I explain you what are particle systems, okay? So I'm changing now. I hope my computer, okay. Can you see it? Yes, not very well. The colors are completely different. All right. So what I want to explain is this connection between what we call the microscopic world, so the world of particles, and the macroscopic one, the world of equations, the world of solutions to some equation. And what I will show you is how to deduce one universal law, but there are many others, in fact many others which people cannot prove, cannot derive, from this random movement of particles. So to put it in a context, this comes from, well, is inside, let's say, the branch of statistical mechanics. And the idea is the following. Imagine that you are in this room and you have a gas. You have your gas and you say, I take a loop and I try to see how the particles are moving. I cannot give a precise description, and I don't want, in fact, to say that the probability that I find this particle at this specific position is something. What I want to say is that, what do I see with my eyes? Can I describe what I see with my eyes by means of some equation? And so according to Boltzmann, to answer to this question, we should do this list of things. So first thing, what are the equilibrium states of my system? And then I will explain, well, I hope if I have time, to say what is these equilibrium states from the mathematical point of view. What does it mean, an equilibrium state? Then we should characterize them through the macroscopic quantity that I have an interest to understand, the density, the energy, or whatever. And then we make the analysis of the system out of equilibrium, which is much more complicated. So the physical motivation is like this. Suppose we are here in this room, there is a gas, you take a loop, and you look at the particles. And now I say, well, I have these, let's say, here is just 2 dimensions, but whatever is the dimension, you fix a point, I call it Q, I hope that you can see. And I fix this point Q and I say, well, I take a neighborhood very small from the macroscopic point of view, but very large at the level of the particles. And since I have too many particles there interacting, I assume the system is close to some equilibrium state, so I did my job according to Boltzmann. And that equilibrium is characterized by a function which depends on the point that I chose. All right? Now I let time evolve, so I go out of the room, I come back, and I ask the same question. I fix a point, a neighborhood, the system is close to equilibrium, but this equilibrium now is characterized by a function which depends on space, the space I chose, but also the time that I'm making my observation, that I call t. And what is assumed is that this function, so you can make an experiment, go out of the room, come back, and 1 to 2 times, 3 times, and take, let's say, and you look at this function in different times, and you say, maybe I can deduce an equation for this function. And what is assumed is that in fact, this function evolves smoothly according to some PDE, to some partial differential equation, which is called the hydrodynamic equation. Okay? So this is the question. What is the macroscopic law, the equation, that describes the space-time evolution of the conserved quantity in the system? All right. So particle systems, or interacting particle systems, they were introduced in the mathematics community by Frank Spitzer. But they were known and they were widely used before by physicists and biophysicists. And Spitzer gave lots of contributions in probability, so I just put here some of them. But in fact, so what is a particle system? And basically what we have is, let's say, a collection of random walks and Poisson processes. So I try to introduce you very quickly what is a random walk, an example of a random walk, and a Poisson process. And then we put it together. So a random walk, I think everybody knows in this room what is a random walk. Suppose that you toss a coin many times, you just flip it, and you say that when xn is, so you are in the nth experiment, and if you have heads, you say that xn is equal to 1, and if you get tails, you say that xn is equal to -1. And you fix x0 to be 0. So if you make a drawing, you can imagine that x0 equal to 0 is like you are fixing the initial position of your walk, of your particle, let's say. And every time you flip the coin, either it goes to the right if you give a jump of size 1, or you go to the left because you get tails, all right? And you keep doing this. So if we want to denote the position of the walk at time n, and look that this is discrete time, I call it Sn, all right? Which is just the sum of these results of these experiments. So the question is, how far is the walk from 0, from its initial position? Well, the average is 0, and if you want to know this mean average distance, you compute the variance, and so this variance, let's say this distance should be of order square root of n. But can we really compute this in hands? So let us compute this probability. And I say, well, okay, maybe you cannot see everything, but you can imagine it's almost everything. If the walker gives an odd number of steps, then it should stand at an integer odd position. So you have this result. And then you say, but if the walk gave an even number of steps, let's say 2n, it goes back to 0 if what? If I gave n steps of size 1 and n steps of size -1. How many ways can we do that? Well, from 2n, you choose n, right? Okay, this looks more like a classroom, a lecture, but it's just to show you that the first time that probably you have seen the passage from micro to macro, you already seen it in a very, let's say, in the second year probability and statistics lecture. So I say, all right, the probability that you find the walker after 2n jumps at 0, where it started, is what? Well, it's the number of choices that I have to fix where I'm going to give the jumps of size 1 times the probability, which is just a half because I'm assuming that I have a regular coin. All right, and then I say, okay, what do I do with this? So now I go quickly. In fact, you can compute it, and you can even compute more. You can show that the probability that you find this walker, this random walk, after 2n steps in some interval, and when you take the limit in n, you can approximate it by this quantity. And when you look on the right side, what is here is just a density function of a Gaussian random variable. So basically, you are going from a discrete process, and also a discrete process in time, and you are getting some continuous distribution out of it. And this is what is called the central limit theorem, one of the basic ones from the Moivre and Laplace. So you see this, let's say, extracting a continuous distribution from a discrete system with discrete time and discrete space is already here, right? It's already here in this result. All right, what is a Poisson process? And now we are in continuous time. So imagine that you have the following experiment. You are at a call center, and you keep noting down every time. So you start your day, you are going to work, time 0, and you look at the telephone, and whenever you get a phone call, you mark the time at which you got a phone call. Time t1, you receive one. Time t2, you receive the second call. Time t3, the third call, and so on, right? And I'm going to show you a picture just after. So imagine that I just put here some crosses every time there is these jumps, okay? Because they will be important later. All right, so there are some assumptions for these Poisson processes. And these assumptions are basically these three. I will read them. Stationary increments means that the probability that you have k calls in the time interval, this time interval here, only depends on the length of the interval. Independent increments means that if the calls come in in intervals of time which are disjoint, they are independent. And more importantly, two calls don't come at the same time, right? We can only pick the telephone once, and we're not quantic, right? So how to use these two different, let's say, random walks which have, let's say, a discrete time, and they evolve in discrete space, and Poisson processes which evolve in continuous time. So how do we cook up particle systems from there? So I'm going to give you an example. So now my discrete set of points is just 0, 1, 2, 3, 4, 5. I fix the initial configuration of my gas. What do I do? This is one possibility. There are many others. Toss a coin. If you get a heads, put a particle. If not, leave it empty. Do this, and you fix. So you have to toss a coin for 6 times, and you get to this initial configuration. All right? It's clear? Now, okay, now it's messy, but I will try to explain. what you see here is the initial configuration that I fixed according to that experiment. Now, I tell you that if I know all the marks, you remember these crosses that I mentioned about the Poisson process? If you know all of them, you cook up the evolution of the dynamics. This is a particular one. So how do we read it? You let time go down, and you look here at the first time that you see a mark. It's here. So this means that my dynamics is just swapping this particle. So look at here. What happened from here to here? This particle moved to this position. And now you continue. How do I read next? Well, I go down. The mark that I see, it's that one. So if it's this one, it means that this will jump here. Look at the difference between these two. This particle came here, and so on. So once I give you a collection of independent Poisson processes which are connecting, in this example, 2 consecutive points, and I give you the initial condition, everything is known. All right? So you know the whole evolution of the process. And this is a particle system. And I'm going to give you 2 examples of the most classical one. So this one is called exclusion process. And exclusion means at each site, and here I'm taking Z, but you could do it with any kind of a graph that you want, or even a fractal. You put a particle according to some rule. So suppose this is our initial configuration, and I say a particle jumps from X to Y with a certain probability. This one, that is generic, depends on the size of the jump. But you only jump if the site is empty. Otherwise, you stay where you are because you cannot have piles of particles. So this, okay, maybe you see these arrows here. So when you see these arrows, it means that here, if I was looking at the description with the marks, I have a ring of a Poisson process between this guy and this guy. Since this position is empty, the particle jumps, right? So here it's much more complicated than this previous construction here, because I was only allowing jumps to nearest neighbors, and now I'm not. I'm allowing long jumps. And this, of course, has a consequence at the level of the equations that we get. So this clock is ringing, particle will jump over there. So this is what happens. This is not allowed, as I told you, because they cannot pile. And this cannot happen. Remember the story about you cannot have 2 calls at the same time? Here it is. Let's say it can happen, but with probability 0, which for probabilists is the same as saying that nothing happens, right? Zero range. So now you could ask me another process for which I can have piles of particles. So let me tell you quickly. This is an example. It's called zero range because particles can jump from X to Y, wherever X is and Y is, but according to a function here, G, that only looks at what happens in the place where I am departing, okay? And that's the reason why it's called zero range. All right, so this would be what would happen. You would see this, and you would see this. All right, one important thing is that whatever is the dynamics that I'm defining here, the quantity of particles is conserved, but it evolves in time, right? I'm not destroying or creating particles. I'm just moving them in the discrete space. So I'm going to show you a simulation, and let me explain you quickly because I will run the 4 of them together. The difference is, above, you have symmetric rates, which means particles jump to left or right with probability 1/2. Below, you have asymmetric rates, which means that you go to the right with rate 0.9 and left with 0.1. Okay, the difference between, up and down, left and right is what? The initial configuration. So in this case here, the initial configuration is that you have 1 particle at site 1, 2 particles at site 2, 3 at site 3, and so on. And here we have everything empty, 100 particles here, and everything empty. So let's see what happens. And I'm considering periodic boundary conditions. And you will see that below, you see a preference, right? Particles are really going to the right. And the question is, okay, they are appearing here because I told you they have periodic boundary conditions. But one of the questions then is, okay, now it stopped. Can I find an equation which tells me that whenever I stop, I have a function here which very well is approximating what I'm seeing? Is there one equation that does this? Yes, the answer is yes, is what is called the hydrodynamic equations. I will not explain how to deduce them because it's quite complicated and it's not my goal today. I put here just a very short list of types of equations that one can get, the heat equation and more complicated equations. And let me show you just a simulation quickly. So here I'm going to run again the 2 simulations you have seen before, but here you see some red line. I hope that everybody can see the red lines. Yeah, these red lines. So this means that I am simulating at the 2 times. So this is the solution to some equation, and this is the system with symmetric rates. And try to see, the idea is this function approximating the distribution of particles? I hope you agree that they are. But you already see that the system is not exactly on top of the line. There are fluctuations, you see? This goes up and down, so there are some fluctuations of the microscopic random system around this deterministic solution. And this is another question. So this goes to the topic of fluctuations and universality. I think I have 3 minutes, right? Yeah. Okay, so I show you again, here one of the problems, now that you understand the hydrodynamic limit, is to control the fluctuations of the random system along, for example, here, just a constant function, how these fluctuations are described. And now we go to the topic of universality. So let me see if I can show you. These solutions here in the fluctuations, they are solutions not of a deterministic equation, but something which is stochastic. And there is a law, so I'm showing you this because this is one of the works that I did with some colleagues, and in fact is the subject of this ERC grant. It's the following. There is an equation which is called the KPZ equation from Cardar, Parisi, and Zhang that was proposed in 1986 to be a universal law which is behind these random growth patterns, as for example bacterial growth, coffee ring effects, hailstone deposition, which is what you're going to see here, and tumor growth. And so imagine that you are on a car in a very, very drastic winter day, and you have these particles, these ice particles fall. So imagine that this is like the front glass of the car, all right? And what you see, I will try to put it to work, but maybe you tell me if you can see. Can you see? Because I'm doing it very slowly, because I want to show you that the ice particles, they touch and they glue. You see this? Yeah. Can you see it? They come, yeah? Is it clear? They come, and whenever they see another particle, they stick to it, right? And one of the things, okay, if we could do that, if we could get out and make a zoom out of this picture, what we would see would be an interface line which is separating the part where you have ice particles from the part which is clean, let's say. You will have this line, very regular, which is separating these 2 phases, let's say. And this is the line which is universal, which appears in all these phenomena that I mentioned. Another one is this. You take a paper sheet and you just burn it here. And when you look, maybe I show you, and when you look at the interface, between what is burned and what is not, okay, maybe you don't see it very well, but this line here is exactly the same that is appearing in the previous experience, all right? So this is a universal law which is related to some game. So just let me show you quickly. I think everybody knows this game, which is the Tetris game. But let me show you that this is the pattern exactly that you would see. Remember the experiment with the glass window with the ice particles is exactly the same kind of line. They are the same thing. So the same law appears in a very different context. All right, what is this? So let me show you my okay. So this is a universal class, the class which is here in the sticky block deposition. Why sticky? What is the difference between these 2 games of Tetris? This is the usual one, you know, right? Blocks come down, whatever, if they have blocks close to them, they don't touch. But here in this case, what happened? Maybe I should go back. Here you see that the blocks are, it's not very easy to see, but the idea is that if a block comes, but there is a column, the next column, which has already another block, it sticks. So you have holes, all right? And that's why these holes appear. All right, then, okay, I'm finishing because I think I'm out of time. All right, so let me tell you that this belongs to some universality class, which is people called KPZ fixed point. There are many others. This is what is called Edwards-Wilkinson or Gaussian fluctuations, which is the one that appeared in the central limit theorem that I showed you in the beginning. And there are many equations that link the 2. I put this as a cloud as if it was like different universes. And you can link the 2 by some equations by tuning some parameters. And one of the things I did with colleagues was to derive this, not this, but up to here, from many different microscopic dynamics. There are many others, so maybe you see here just a cartoon with the connection that I just showed you, but there are many, many others. And this is just predictions by physicists. So physicists, which I like very much to work with, they kind of feed us. They give us problems. Look, we predict this. Can you prove? The only thing which is proved so far is this connection, and this. But many others are supposed to be true, but it's very difficult to prove. All right, so I finish. If you want, and if you have any interest in working in this type of things that I just mentioned here today, okay, these are some things that maybe you can ask me at the end, so maybe I just go straight because I think I'm completely out of time. And in case you want to do a master at our department, so let me just tell you quickly, we have 3 master degrees, you see here, in applied mathematics and computation, in engineering and data science, and information security and cyberspace law. You can see some videos, I will show you where. And all the coordinators of the master are here. They are happy to talk with you and clarify all your doubts. So let me just do 2 things to finish, and I promise, oh, sorry, I will not take so much time. Yes, it's here. So if you come here to this webpage, you can see these videos of my colleagues, and you can see different research projects. So you can just come to this webpage, scroll down, and see the videos. They are short, 15 minutes. And, well, maybe you have interest. There is tomorrow this conference here called Lisbon Young Mathematicians Conference 2024. And I have a student, okay, which is not here, but she's going to talk about, okay, let me see where it is. It's here, exactly. Oh, maybe you cannot see. From particle systems to PDE. So in case you want to know more how we really deduce these laws, these equations, go to her talk. Thank you very much, and I'm very sorry for being late.
Thank you very much, Professor. So I would ask if anyone does any questions about this session. Anyone?
Can I tell a story about questions?
Yes.
Yes?
Yes, of course.
So when I did my bachelor in Porto, there was no way that a student would interrupt a professor in the middle of a class to whatever was the reason. No way. People used to call, in fact, you know, I was a tutor. I told you my story, right? I went to the PhD, but before I was a student, and I was a tutor for a semester. And my colleagues, which were just 1 year younger than me, used to call me, how is I say it in Portuguese, Excelentíssima Senhora Doutora, which is too much, no? 1 year difference. And when I went to Brazil, one of the things that I like is that people interrupt the classes, people ask questions, people point out mistakes in the board. So if you have seen any mistake in my slides, or if you have any question about whatever, no, didn't work.
What is your dream in terms of...
You came late. I showed my dream.
Yeah. Yes.
Well, I have many dreams, but maybe just
The
putting the feet on the ground.
Don't put.
Just to create a team of people working in this in these problems, because they are very nice. And we really need to interact with people with different skills, some people from PDEs, people from SPDEs, theoretical physicists, even people doing simulations, which are very, very important. The simulations that I showed here, that are very hard to do. And I think this would be something which, it's very nice. It's very nice if we could have this mixture of people, young people, motivated people, to work on this. It's my dream. It's to create a team and also to change the offer in probability in Portugal. This is something I want to do.
What should be that offer?
All right, now we go to a very gray scenario.
Ask for questions.
No, I think we should do something different.
How can students contribute for that change?
Yes, I think a student, in fact, in Portugal, I think it's kind of, in fact, I think it's transversal. The world is changing a bit because probability now, let's say, the first medals field in probability was just in 2004. Wendelin Werner was the first. So, you see, 20 years ago, I think probability was never recognized as, let's say, a field by itself. Which is, and somehow, I think, only recently people look at it differently. And probability can be anywhere. You can put probability in mathematics very easily. With all the fields, you can try to take out the deterministic aspect of what you are doing and make it more complex. And my feeling is that to do this, of course, you need to introduce, let's say, the background, which is a course in measure theory, which is like the ground stone. If you don't have that, it's very hard to do it. And I think we should change that, is really to start to tell people, look, there is here probability. First you learn measure theory. It's one of my, yes, it's one in one of my slides. You have measure theory, and then you do probability on top of that. And then you can do very nice things. But then my feeling is that the students end the bachelor, and they don't have time to see many things. They see many things in probability, but they could see more. I think they could see more. I think they could see other topics, in fact. I think we should change that.
Some seminars.
Yes, we have lots of analysis, geometry, maybe some more emphasis on probability. But it's not the problem in Técnico, it's Portugal. I think it's world, in fact, because as I mentioned, 20 years ago, the first Fields Medal, so.
Okay, so now I have a question.
All right.
What does it take for a student to work with you in this field? What is the background needed?
Yes, it's in one of my slides I show you. So the thing is, so in fact I do not have many of my students. I have 3, I think, that are doing the bachelor, the course. Okay, let me see if I find my slides first, but I had one. It's here. It's before the masters at the department. So what you should do if you want to, so let me tell you, I supervise some students at the level of the master, and usually what I ask them is to do this course in measure theory and stochastic processes at the level of the bachelor. Then there is a course in probability theory, functional analysis, and PDEs that they can do at the level of master. And there is a course, in fact, there is another one which I didn't put here, but there is a course in stochastic differential equations that they can have at the doctoral program. And the master is flexible, so you can do this course, which is for the PhD. You can actually do it while you are a student at the master. And what I tell them is to do this and to try then, of course, that after this they have to do other courses for which we do not have, let's say, offer, because only few students would take them. So I just do some tutorial course with them. So I try to teach them and tell them what to read. And these could be topics for a master thesis, the 2 that I put here. But it's true that they feel a bit of, because you have to learn many things before really going to the problems. But I think it's normal.
And could this be involved in a real world situation? So with this background, with these degrees, could a student only be a professor here in the university, or could this be, what do you have as an example of a real
many students that do a PhD in probability in general, they have many. I don't know. I mean, people going to academia. It's true that it's much more complicated because the academia is complicated. But people can get jobs in the banks, in the insurance companies, very easily in the actuarial world, and very well paid. I think the actuarians are like the second or the first best job in the world. So people with let's say with this type of PhD, yeah, they can do
whatever they want.
Yeah, basically whatever they want. I was not going to say that, but yes, because they have different skills and they touch with different fields in mathematics. This is one thing which I think is very nice because they really learn different things
in the area of mathematics.
Yeah, and now then you can go to data science now and to whatever.
So I would ask once more if does anyone has any questions that you want to ask about?
Yeah, go.
You do?
Yeah.
No, they are afraid to ask.
Yeah, don't be afraid. No? Okay. Maybe the students have some questions for you?
Does my students have questions? Or my colleagues have questions?
Do you have questions for us?
I can ask.
What about joining heavy tails? Because you only have
No,
notion.
I have heavy tails. I have. It's true, and here, okay, I didn't mention, but these processes here, these Levy 5/3, these are heavy-tailed processes. So what we do to get them, okay, there are many these are universal laws, but one way to get to these laws is not only by allowing particles to give long jumps which are heavy-tailed, but in some cases there are some models which we don't understand very well, which have more than one conserved quantity. In fact, I showed you a very specific scenario, but it can be, you can have a dynamics which conserves more than one quantity. And then you don't have one equation, but systems of equations. And in this case, there are models for which the dynamics is just two neighbors, for which one we could think that we would get a Gaussian, a Brownian motion. But no, we start to get these Levy processes. And there is this one here, which is very nice, which is a Levy process with a parameter which is given by the golden ratio. And why it appears, it's still, nobody got it. So I'm working on, I have a model that we're trying to get this process, but it's very hard. But it's true, we can get, and actually to fractional equations as well.
Well, I was wondering whether the students, if they want to go to a master in mathematics, I'm wondering what should they choose in order to become your student? And what is your process? What do you value for a student to become part of your
What does a
team?
professor value
And
as a
what
student
advice on how
to
choose
work
a
with
good
her?
supervisor?
Ah,
Or
yes.
a master or even a PhD.
Or even a PhD, right. So I think the most important is that you really get passionate about whatever you're going to do, because PhD is a very complicated period. It's 4 years in life that you are supposed and you have to do, especially in mathematics, you have to do something original. But it's not just something, it has to be something, you know, substantial. And sometimes it can happen, and this is something I always tell to my students, I do not give them one project. I typically give one or two, and I actually invite collaborators from this big list of collaborators that I have. I usually ask someone, do you come and want to help? Because I think it's great when they can discuss with different people, with different backgrounds. I think it's nice. And I always try to give different problems, because sometimes maybe I'm naive and I think that they can do it because they are very good students, and they cannot, because we find a problem that we didn't expect. And then if they only have one PhD problem, that can be very complicated, because what do they do? No? I mean, so what I usually tell them is that try to read as much as possible. I tell them you have a project on these, and I try not to have many, different projects, but not so different, more or less using the same type of tools. I have supervised, I think, probably 10, maybe 10 PhD students, and I was really fortunate because my PhD students were very strong, so I never had problems, as I hear that some other people have. I never had. And I have one which is really very good. In fact, he defended 2 years ago here in Técnico with the highest marks, which I think is really fantastic. And for master students, so this is what I actually tell them. If you want to work in this field because you like it, one of the things that I would like as well is to convince not only students and, let's say, master students and PhD students to work with me, but also colleagues. It's something very important, is to interact with these people from the different fields of PDEs. So usually for master students, I tell them, look, try to do these courses. This is like the minimum that you have to do. And of course, there is something else later. But then what I do is just, I do some tutorial courses, and I explain to them what they should learn. What else was your question? You asked me something more, because it was...
What do you value in a student to make them come to
What the professor values as a
persistence.
student.
Persistence, of course, knowledge. But persistent, I think, is it's one of the characteristics I think a mathematician has, is to be stubborn. So you have really to, because you face many problems sometimes, that you can give up. Another thing I tell my students is that maybe you give up of your problems for maybe 5 years, maybe 10 years. I have projects that I started 20 years ago, and they're still not finished. And one of the things I like to do, and I tell them to do, is to revisit your problems, because you are different, you learn. And at the time that you look at, the first time that you look at a problem, you didn't know how to solve it, doesn't mean that maybe 10 years after you still don't know, maybe you know. And this happens to me a lot, that I go back and then I say, wait, but what I used in some other place, it fits here and it solves the problem. Another thing which happened to me while I was still a PhD student, and that's why I recommend people to go to conference, that's why I mentioned that people should go to ICM, which I think is really a fantastic event, is that sometimes you have a problem, you have your PhD problem, a master problem, whatever, you have a problem, a research problem, and you don't know how to do. So you get, in mathematics, it happens to me a lot that I'm super happy in the day that I solve a problem. The day after, I find out that it's completely wrong, and I got completely depressed, and that's how life goes. That's the life of a mathematician. But sometimes it happens that you are at a conference, and this happened to me, in fact, twice, now that I'm thinking about it, twice. One day, I was at a conference, and the guy, a professor from US, somewhere in US, was talking about some problem. I look at that and I said, wait, if I map this to that, it solves my problem. And then I went, I sat down, I talked to my supervisor, say, yes, it works. Great. Another time, I was at IMP at the time, and there was this mini course of Wendelin Werner, one of the persons that got this Fields Medal, and he was talking about percolation, some problem, and at the same time I said, no, wait, these can be used in my project, and it solves the problem. So sometimes going to a conference which is not specifically from your field gives you lots of ideas to solve your problems. So I also suggest this to my students. I think it's very nice. Don't be afraid, talk with people. Sometimes many people, like the story I was telling, in Portugal when I was a student, we didn't talk to professors face to face. And I think it's important, you talk, even if you say mistakes, it's better to say, it's better to discuss, it's better to change ideas than to just, stay in a hole. I think it's nice to socialize in maths, and I think this is why I think networks are very important. So this is the advice. I think I don't give any, well, maybe I give more advices to students. I think are more the most important. Yeah, especially for PhD, I think it's a very difficult period. 4 years of research that sometimes doesn't go well, sometimes it does.
Patricia, you mentioned the first Fields Medal on mathematical probability was 20 years ago, but after that, almost every time there is one probabilist. Do you have, and even the Abel's Prize now is also. So do you have a reason for that, for this trend?
I think it's that. I think probability in the past was not seen really as a real subject. And it started with Wendelin, with all these discoveries, with conformal theory. Then I think it was Smirnov just after in 2008, could be. I don't remember, okay. Smirnov, then Heider, and then Ugel 2 years ago. I think it's because of that. I think probability, people see probability in a different way. Now, I don't think that it will continue to be like that. Maybe we'll stop having prizes in, Fields medals in probability because maybe, I don't know what's going to happen. But I think it was because of that. It was never seen, first it was always seen as applied maths. And I think it was never really seen as a potential, a course with potential, a discipline with potential to touch other fields in mathematics. And people see that now. People see that probability can be used, and it is used, in different fields in maths. And it's making revolutions in mathematics. So I think it's very nice to study probability.
I just wanted to ask.
Very good, Vicente, my student. All right.
If you happen to have research grants for the master students in probability.
I do.
That's not only in this area, this is more general to Técnico, but if that's something that happens.
So if anyone is interested in working with me, I have grants to offer. I have this. Okay, let me tell you quickly. I applied to the RC grant. I have one. I had one. It just finished last November. But I applied again to the second level, which is the consolidator. So the first one I got was a starting, and now there is consolidator, and then there is advanced. I applied to consolidator, I didn't get it. I tried twice, didn't get it. But then I got a grant, first grant, which I think it's very nice from the FCT, our National Science Foundation, which is really recognizing, and I think it's very nice. So I have a grant which I can offer, master grants. So if you have interest, let me know.
And I think there are now opening your research center just opened position for master students.
Ah, really?
Right?
I didn't know.
It was sent to the students.
Good.
To get information about research fellowships for
Okay.
master students.
So if you have interest, let me know. There are these grants from the research center, but I also have from the project, so. Obrigada, José.
Okay, so if you don't have any more questions, thank you once again for
welcome.
the interesting talk. We end up this 8th MasterTalk session. Don't forget that we have another one. The next one is from the Department of Mineral and Energy Resource Engineering with Professor Leonardo Azevedo. We also will have the open day in Técnico in the 20th of April, so next week. If you want to come, we welcome you to do so. And don't forget that now outside you have the opportunity to talk with the coordinators from the masters in the Department of Mathematics, the 3 ones that the professor mentioned. And you can also ask for student support and many other stuff. Okay, so thank you very much once again for joining us, and see you next time. Thank you.
Thank you.